So we want to continue with a discussion on inner products of vector spaces. Okay, so for Rn, vector space Rn, we saw your dot product, right? So the dot product between two vectors, say u1 v, right? Where u is u1 to un and v is v1 to vn. The dot product as defined this way, right? And we can also define dot product as, once we regard in u and v as row vectors, right, then your dot product we can write as matrix multiplication u times v transpose, right? Okay, but this is your normal dot product that you would have seen already, right? And a dot product is an example of an inner product, right? Okay, and we also saw for Rn, right, if I have inner product defined as u times a times v transpose, where A is n by n positive definite matrix, then this is also going to be an inner product on Rn, right? And we saw for polynomials of degree at most n, right, we can define an inner product via integration, right? So here I have the vector elements in Pn being polynomials, and your inner product of the polynomials. What you do is you multiply your polynomials and you integrate between 1 and minus 1, right? Okay, and this is an inner product, sometimes called L2 inner product on Pn, right? Okay, so we saw some examples of inner products, and let's continue, right? Okay, so if I have an inner product space, right? So what an inner product space is, an inner product space is a vector space together with some inner product, right? So for example, Rn, when you're using standard inner product on it, that's an example of an inner product space, right? So a vector space together with some inner product is inner product spaced. Okay, so I have an inner product space, and I want some definitions here, right? Okay, so the first one is I want to define what a length of a vector is with respect to the inner product, right? That's defined on it, right? Okay, and how you define length is you take the inner product of the vector with itself, and then you take square root of that, right? So already that inner product of a vector with itself is always going to be bigger than or equal to 0, right? So square root of this quantity over here will be well defined, right? Okay, so for example, if I have vector space R3, right, where I'm using standard inner product, then according to this definition here, the length of a vector, and I'm just using arbitrary vector A, B, C, and R3, right? So your length of a vector would be inner product of the vector with itself, and you take square root of that, right? This inner product that we're talking about here is standard inner product, right? Okay, and its standard inner product is just dot product, and we saw already that we can uh, calculate dot product this way, right? Row vector times the row vector transpose, right? Okay, so here in this case, the row vector is ABC, and column vector is you take V and you take the transpose of it, right? So what we're doing is you take an inner product of V with itself, right? Okay, so I have my row vector here, and then I have column vector, and then what I do is I multiply row vector against column vector, right, in the usual way, and what I'd get is a squared plus b squared plus c squared, and then square root over here, right? And this gives me this formula, square root of a squared plus b squared plus c squared. And this is your standard idea of length of a vector, right? So if you use a normal inner product, standard inner product, then what your length is your length is really just your normal definition of length, right? Square root a squared plus b squared plus c squared, where a, b, and c are your components. Right, so let's see a next example of this, right? Probably a little less standard, right? So I have a vector space which is polynomials of degree at most 3. I have this polynomial in it, right? And I have uh, L2 inner product defined on this vector space, right? It's defined that how I get the inner product of the polynomials is I multiply them together and integrate between 1 and minus 1, right? Okay, so the length of this vector over here, which is a polynomial because the vector space is polynomials, right? The length of this vector, how you get it is you take the inner product of the polynomial with itself, right? And then you take the square root of that, right? Now the inner product of the polynomial with itself, right, is when p is equal to this x squared plus x plus 1, and the q is equal to the x squared plus x plus 1. So what I'm going to do is I'm going to multiply both these together, right? So and then I'm going to, my definition of the inner product here is that this product, which is a function of x, I'm going to integrate between 1 and minus 1, right? Right, so this here is just normal integration. Here you multiply this out, right? And you integrate between 1 and minus 1. When you do that, you're going to get 22 on 5. But remember, the length is inner product of vector with itself, right? And then you take the square root of that, right? So here we take the inner product of the vector with itself, and then you take the square root of it. So it's a 22 on 5, and square root of that would be square root 22 on 5, right? So in this case, the length of the polynomial x squared plus x plus 1, right, with respect to this inner product over here is square root of 22 on 5. Alright, so next definition that we want to look at is if I have two vectors u and v, and if I work out the inner product between them and it turns out to be equal to 0, right, then you say that the vector u is orthogonal to v, right, with respect to the inner product that you're dealing with, right? Okay, and we saw examples of this already, right? So the easiest example is if, for example, your vector space is R2, which is the plane, right, and you're using standard inner product, which is dot product over here, right? So here, well, by now you should know what the dot product is, right? You just multiply in corresponding components, right? Okay, so I have vectors u and v. I take the inner product of these here, right? And in this case, because this is just a standard dot product, I'm going to multiply 1 times 1, 1 times minus 1, and add that. So I get 1 minus 1, which is 0, right? So this is an example of two vectors here that are orthogonal to each other, right? And the idea of the orthogonality here is the normal idea of orthogonality that you know. These vectors are at right angles to each other, right? Because it's normal. It's your normal idea of orthogonality because the inner product that you're using is really standard dot product, right? Anyway, so these two vectors are an example of orthogonal vectors, right? U is orthogonal to V, right? Because when you work out the inner product of U and V, you end up getting 0, right? Okay, and this situation here we can sketch, right? Your vector U is this red vector here. The vector V is your green vector over here, right? And you notice that these vectors U and V they lie in the plane, and they're at 90 degrees to each other, right? Okay, so your orthogonality for standard inner product or dot product, right, gives you your normal idea of what orthogonality is, right? That your vectors are going to be at 90 degrees to each other, right? Okay, now that idea of the 90 degrees, strictly speaking, it only really holds if you're talking about standard inner product, right? Okay, so let's see an example of orthogonality when you're not looking at for something that is not standard inner product, right? So vector space of polynomials, right? So I have these two polynomials here that are in P3, right? And I want to show that these are orthogonal, so polynomial x and polynomial x squared minus 1, right? These are orthogonal with respect to the L2 inner product, right? So remember, this is how you define the L2 inner product for P3, right? What you do is the polynomials, you multiply them together and you integrate between 1 and minus 1, right? Okay, so right, so we're looking at these two polynomials here, x and x squared minus 1. So in order to work out the inner product here, we multiply the x times x squared minus 1. And then you integrate that between 1 and minus 1, right? And you need to do the integration, but when you do this integration over here, this integral will turn out to be 0, right? Okay, so these polynomials here, x and x squared minus 1, are actually orthogonal to each other, right? With respect to this inner product over here, right? Perhaps it doesn't really have a nice geometric interpretation, right? But given how this inner product is defined according to the definition of this inner product, these polynomials are in fact orthogonal. Okay, so we just saw examples of two vectors being orthogonal to each other, right? So the easy case to see is if I have these two vectors in the plane, 1, 1, and 1 minus 1. Uh, and if I'm using standard inner product, which is dot product, right? These vectors are orthogonal, and using standard inner product, these are at 90 degrees to each other, right? Okay, so I can, if I have more than two vectors, I have a if I have say three vectors or four vectors and so on, right? I can define something called mutual orthogonality. Okay, so if I have some set of non-zero vectors such as this over here, right? So notice here in R3, right? I have three vectors, right? 1, 0, 0, 0, 1, minus 1, and 0, 1, 1, right? Okay, and if you notice that vector 1, 0, 0 is in fact orthogonal to 0, 1, minus 1, right? You can check when you take the dot product of first vector with second vector, you'll get 0, right? Okay, and second vector is orthogonal to the third vector over here. If you take, and here I'm using standard inner product, right? Okay, so if I take dot product of second vector with third vector, I'd also get 0. And if I take dot product of first vector with the third vector, I'd get 0, right? So if you have a set of vectors, in this case I have a set of three vectors, and I looked at any two non-equal vectors in that set, right? And if when I work out the inner product for any of those two, I get 0, right? Well, then what? In other words, if any two non-zero vectors are orthogonal, right? And that holds for the entire set, right? Then this set over here is said to be mutually orthogonal, right? Okay, so one more time, right? I have a set of vectors here, right? And if I take any two different ones, right? And if any two different ones, I always get that they're orthogonal, right? Then that means your entire set of vectors is mutually orthogonal, right? So these three vectors here are mutually orthogonal because with respect to a standard inner product, which is dot product, if I take any two and I work out the dot product, I will get 0. Okay. Okay, so let's graph these three vectors here in our tree so that you get an idea of what the mutual orthogonality looks like when you can actually visualize it, right? Okay, so these black vectors here, these three vectors, 1, 0, 0, 0, 1, minus 1, and 0, 1, 1, right? Okay, so first vector, second vector, well, this is the 1, 0, 0, right? This is the 0, 1, 1, and this is 0, 1, minus 1 here, right? Okay, and what you want to notice is that these are at 90 degrees to each other, right? It may not be extremely easy to see, but I guess if you project appropriately, you see, well, okay, these two are at 90 degrees to each other. If you spin this around like this, okay, you'll see that these two are at 90 degrees to each other. And if you spin this around like this, you'd see that these two are at 90 degrees to each other, right? Okay, so any two vectors, I have three vectors over here, and if I look at any two of them are at 90 degrees to each other, right? A next example of a set of mutually orthogonal vectors would be these polynomials here in Pn, right, where the inner product is the L2 inner product. And the L2 inner product, remember, was defined by this sort of integral here, right? You multiply your polynomials together and you integrate between 1 and minus 1, right? Okay, so these polynomials here, the 1, the x, and the half, 3x squared minus 1, right? these are mutually orthogonal, right? It would take some work to show it, right? Okay, so what you need to do is if you wanted to show it, you check, you consider any pair, right? And then you work out the inner product of any pair, right? So for example, with the x and the half 3x squared minus 1, right? What you need to do is you need to multiply them together, right? So this is the x over here, and this is the half 3x squared minus 1, right? And then you need to integrate them between 1 and minus 1, right? So this is the integral displayed in Maple, and this is when you actually evaluate this integral. When you evaluate the integral, you in fact get 0 over here, right? Okay, and you can check if you take the inner product with the x with 1 or the one with the half 3x squared minus 1, right? In those two other cases, the inner product would also be 0, right? Okay, so this is an example of a set of mutually orthogonal vectors in Pn with respect to L2 inner product, right? All right, so a next set of mutually orthogonal vectors, in this case the vectors are continuous functions, right, would be these over here, right? So 1 cosine 2x, right, cosine 3x, and so on, right? And then sine x, sine 2x, sine 3x, and so on, right? So this over here is actually this is not a finite set, right? The number of elements in here over here is not finite because you have any cosine, you have any harmonic of cosine and any harmonic of sine over any integer harmonic, right? Okay, so this here, if I consider, well, these are functions, these are continuous functions belonging to the vector space of continuous function between minus pi and pi, right? And for these functions, I can define an L2 inner product where similar to the one that I had with polynomials, right? But what I'm doing now is, again, I'm multiplying the functions, but I'm going to integrate between pi and minus pi, right? And we can show that these here, right, these are mutually orthogonal with respect to this inner product over here. You just need to check the various cases, right? I'm not going to do it formally for you, right? But I'll just show you a couple of examples, right? Okay, so for example, if these are mutually orthogonal, right? So what it means is if I have two different ones, right? So if I have two different cosines, so for example, cosine 2x and cosine 3x, and I integrate that between pi and minus pi, right? When I actually work it out, I'll get 0 over here, right? Okay, so two different cosines would be mutually orthogonal. Well, this is just an example of that, but this would take a certain amount of working. Well, what you need to do is you need to use some addition formula for cosines and sines, right? To show that in general, the integral between pi and minus pi of cosine 2x and cosine 3x, well, once you have different harmonics over here, this integral is going to turn out to be 0, right? But this is just an example of it, right? Okay, and if I have a cosine with a sine, right, such as this over here, cosine 2x and sine 5x, right? If I integrate this between pi and minus pi, right, I'd also get 0, right? Okay, so any cosine is going to be, this is an example of cosine being, cosine 2x being orthogonal to sine 5x, right? And you can in fact show more generally that any cosine over here would be orthogonal to any sine over here, right? Okay, and then, well, if you take inner product of one of these with itself, right? So for example, you take inner product of cosine with itself, right? Which means I'd multiply cosine against cosine and integrate between pi and minus pi, right? In this case, I do not get 0, right? Okay, which is what you expect, right? Because remember that inner product of a non-zero vector with itself is supposed to be bigger than 0, right? Okay, and you see an example over here, right? So the orthogonality holds when you're looking at different functions here, right? Cosine and cosine 2x, say on this example that I did, cosine 2x and sine 5x and so on, right? Okay, so any two different functions over here are going to be orthogonal. So this set over here is mutually orthogonal, right? Okay, and why you care about something like that is, well, you use these over here when you define in your Fourier series, right? And these formula for your Fourier coefficients actually part of deriving these formula using the orthogonality, the mutual orthogonality of these functions here, right? Okay, so the functions that comprise your cosine, which would be constant term cosine, the harmonics of cosine and the harmonics of sine, right? Which are these over here. These are mutually orthogonal, and these the orthogonality of these functions is what helps you derive these formula for your Fourier coefficients. Okay, so let's start talking about projections, right? And start with a case when I have two vectors u and v, right? And what I want to do is I want to project v onto u, right? Okay, so examples of vectors v and u would be these two vectors here, right? So your green one is the v, right? And this gray one over here, this is vector u, right? What I want to do is I want to project, right? So what is the projection, right? The projection is, right? So the projection of the v over here, which is the green one here, onto the vector u, right? Or more precisely, onto the subspace spanned by the vector u, is this red vector here, right? So when you take this green one and you project in the direction specified by u here, right, what you get is you get the red vector over here, right? Okay, so this red vector here is the projection that we're looking for, right? Okay, so let's look at a little more carefully at the definitions here, right? Okay, so I have vectors u and v, right? An example of the v is your green vector here, and I'm dealing with an inner product space, right? So a vector space with an inner product, right? Because in order to calculate your projection over here, notice what you're doing is you're using your inner product here, right? Project v in the direction specified by u, right? So the small u over here is a vector in the plane, right? And taking the span of that small u over here, the vector u, right, gives me a subspace of my vector space, right? So if I take the span of this vector u here, which is this gray vector here, right, going from A to B, right, what I get is I get a subspace, right? So this is the subspace that is spanned by this vector u here, right? And what I'm doing is I'm projecting, I want to project this green vector v onto this subspace, right? So basically what that means is I want this green vector, I want to project, right, in, so and when I project into the direction specified by the subspace big U, right, I'm going to get a new vector, right? So the projection of this v over here into the subspace u, capital U, right, is going to be a vector that lies in the subspace U, right? So it's going to be this red vector here, right? So the projection of V into the subspace spanned by U, right, is going to be this red vector, which actually lies in the subspace U, right? So when you project into a subspace, you're going to get a vector that's actually lying in the subspace. Okay, and how you actually calculate your projection of V into subspace spanned by vector U, right, is using this projection formula, right? And notice your projection formula over here, it involves taking inner products, right? Now I have it, this example here is for vector space R2, and I'm using standard inner product, right? But this projection over here, right, could work in more general cases, right? The V doesn't need to be Rn, and you don't need to be using, say, standard inner product or dot product, right? This would work. This definition is arbitrary inner products, right? Okay, so how you calculate your projection of V into U, right, is you take an inner product of vector V with U, right? You divide by the inner product of U with itself, and then you multiply by U, right? Okay, so let's see an example of using this projection formula, right? So we want to project V, which is 0, 3 over here, right? Into a direction specified by the vector small u, which is 2, 2, right? So you want to project into the subspace span by the vector 2, 2, right? Okay, so vector v is 0, 3, vector u is 2, 2, right? And then what I'm doing to calculate the projection is using this formula here, right? Okay, so I take inner product of v with u. So take inner product with v with u, right? Dividing by inner product of u with itself, right? So 2, 2, 2, 2, right? Okay, and then the scalar over here, I multiply against the vector u, right? So notice what I'm getting over here is when I project v into direction specified by u, I'm getting a vector that is in fact a multiple of the u over here, right? So when I project v into direction specified by u, basically I'm getting a scalar multiple of the vector u, right? Okay, so calculation is the v is 0, 3, so this green one here is the 0, 3 here. The vector u is vector u is this gray vector here, right? So this is vector 2, 2 here, so this is your u, right? So the green one is the v, right? The gray one is the u, right? We work out inner product of v with u, right? And when we work out inner product of v with u, right? This is 0 times 2 plus 3 times 2, right? So I get 0 plus 6, which is the 6 over here. And then I take down here, I'm taking inner product of u with itself. So it's 2 against 2, which is 4, 2 against 2, which is 4, and 4 plus 4, which is 8 over here, right? So this ratio of the inner products gives me 6 on 8. And notice what I'm doing is I'm multiplying by your vector 2, 2, right? So I'm multiplying the scalar over here against your vector 2, 2 over here, right? So I get 3/4 times your vector 2, 2, right? So this is, okay, so this is 3 on 4, and then 3 on 4 times the 2 would give me 3 on 2, and 3 on 4 times the 2 would give me 3 on 2, right? Okay, so what I get is the projection. So this is the v, this is the u, right? And what the projection is this red vector over here. This is your projection. Okay. Right, and why it's called an orthogonal projection is, okay, so this is v over here, and this is the projection of v, right? Now, if I notice the projection of v is starting from your origin over here and going in the direction specified by this, the head of the arrow, right? Okay, so if I go in this direction, what I'm doing is I'm taking the negative of the projection, right? If I'm go this way, right, start over here, go this way. So this is the negative of the projection. And if I add the negative of the projection, right, to the original v itself, right? So this is v here, and this is the projection of v, right? So I'm taking negative of the projection of v plus the v over here. What I would get is I would get this blue vector here, right? Okay, and this blue vector over here, what this is this is in fact orthogonal to the subspace U here, right? So this is where the term orthogonal projection comes from, right? Okay, so if I have a vector in inner product space, in other words, a vector space with an inner product defined on it, right? Then a vector is this vector v is a unit vector if the length of the vector is equal to 1, right? And remember how you get the length of a vector for a given inner product is you take the inner product of the vector with itself and you take the square root of that, right? Okay, so if I have a vector and when I work out its length I get 1, right? Then that's an example of a unit vector, right? Okay, now this statement over here is saying that if I have a non-zero vector, right, and I want to make it a unit vector, right, or if I have a non-zero vector and I want to get a unit vector that is in the same direction as the v over here, right, what I can do is I can take the vector v and I just divide it by its own length, right? And this is alright, so let's see an example of a vector divided by its own length here, right? Okay, so I have this vector v, which is 1, 1, 0, right? And this is an R3. And you want to notice, and here what I'm doing is I'm using standard inner product, which is dot product. Okay, and I take the length of this vector v, right? And the length of this vector is the normal formula for length, right? So I get square root of 2 for the length, right? Okay, so this vector over here, this vector v, the length is not equal to 1, right? So this is not a unit vector, right? Okay, if I want to make it a unit vector, or I want to get a vector that is in the same direction as v, but of length 1, right? What I do is I take the v and I divide it by its own length, right? So I have 1, 1, 0 and I divide by its own length, and the length of v is 1 and square root of 2, right? Which gives me 1 under root 2 and 1 under root 2, 0, right? And this vector here, you want to notice, well, this component 1 under root 2 is the same as 1 under root 2, which is the same thing as going on over here, right? Okay, so v divided by its own length is parallel to the v, right? But the thing about this one is that the length over here is equal to 1. Alright, so let's recall what a basis is, right? If I have, say, a vector space such as R3, right? And if I have vectors here, these set of vectors here, and these vectors are linearly independent, and they span R3, then these vectors here form a basis for R3, right? Okay, so as it is, you should recall what a basis is for a vector space, right? A basis is a set of vectors that are linearly independent and that span the vector space, right? And now what we have is definition of an orthogonal basis, right? So if I have a basis here, right, and the basis has an additional property that the vectors in your basis are mutually orthogonal, right? In other words, for your basis here, if I take any two different ones, the inner product of any two different ones is 0, right? Then that would be an example of an orthogonal basis, right? So this basis over here, and that takes some work to show that this is in fact a basis, to show that it is linearly independent and it spans, right? But you saw how to do that already, right? Okay, so once we know that this is a basis, right, to show that this is an orthogonal basis, what you do is you just check to see that any two vectors, and here I'm dealing with standard inner product, so any two vectors, the dot product of any two different vectors would be 0, and it's not hard to check. If I take the dot product of 1, 1, 0 with 1 minus 1, 0, this dot product will give me 0. The dot product of the 1 minus 1, 0 with the 0, 0, 1, that would give me 0. And then if I take the dot product of the first and the third one, that will give me 0, right? So these are mutually orthogonal, right? And they also a basis. So this is an example of an orthogonal basis, right? So for example, this orthogonal basis over here, the length of this vector is not 1, right? Because the length of this vector is square root of 2, right? And the length of this vector over here is square root of 2, right? The length of this vector is 1, right? Okay, so these here, these vectors, their basis, they're mutually orthogonal, and then they have the additional condition, right? That each one is of length 1, right? And once you have that sort of situation where you have an orthogonal basis, with the additional condition that each one is of length 1, right? Then that would be an orthonormal basis, right? So this here is an example of an orthonormal basis for R3, right? It's a basis to start off with, right? Also an orthogonal basis because any two vectors are orthogonal to each other. Any two different vectors are orthogonal to each other. And then the final condition is that each one has length 1, right? Okay, so an orthonormal basis is an orthogonal basis with the additional condition that each vector has length 1. Right, so let's consider these three vectors here, right? 2, 0, 0, 1, 1, 0, and 1, 2, 2, right? What you want to notice is that these vectors are not mutually orthogonal, right? So for example, if you take a dot product of u1 with u2, right, what you would get is 2 hitting the 1 over here, right, plus 0, right? So the inner product of the u1 with the u2, right, that would in fact be equal to 2, right? Okay, so your vectors here are not mutually orthogonal. Matter of fact, if you take the inner product of u2 with u3, right, what you would get is 3 here, right? So these vectors are not mutually orthogonal, right? So they're not at 90 degrees to each other, right? But however, they are linearly independent and they form a basis for three-dimensional space, right? If you want to take a look at what the vectors look like, right, this is what the vectors would look like here, right? So these black vectors here, right, these are the u1, u2, and u3 here, right? And you want to notice that these are not at 90 degrees to each other, right? Easiest one to see is these two down here, right? Which would be the u1 and the u2, right? Those are in the xy plane, right? And if you project down onto the xy plane, right, you're seeing that they're not at 90 degrees to each other, right? Okay, so your vectors u1 and u2 are not orthogonal. Okay, so I have these vectors here, right, that form a basis for R3 and they're not orthogonal, right? I have this process here, which is Gram-Schmidt, right? What Gram-Schmidt will do for me is Gram-Schmidt will take these vectors u1, u2, and u3, and it will construct from these three vectors over here three other vectors, right? So from the u1, u2, and u3, right, to start off with, right? What I will do is I will get three other vectors v1, v2, and v3, right? And what would happen is that the v1, v2, and v3 would in fact be orthogonal, right? So this is an example of what Gram-Schmidt is doing for me, right? If I have a basis, right, for some vector space to start off with, right, and this basis over here is not orthogonal, right, what I can do is apply Gram-Schmidt to it, right, and what Gram-Schmidt will do for me is it will spit out a new basis here where this new basis is in fact orthogonal. Okay, so this is my starting basis over here that is not orthogonal, right? Okay, so this is not orthogonal, right? And what the Gram-Schmidt will do for me is it will give me something that is orthogonal. Right, and after applying Gram-Schmidt, this is what I get, right? So this is the result of the Gram-Schmidt, right? In fact, the first vector remains the same, right? But I get two new vectors. And the thing is that the three vectors now, right, they would be a basis. And furthermore, that this basis is actually an orthogonal basis, right? You see that the vectors here, the three vectors are at 90 degrees to each other, right? This is a fairly simple case that I constructed, right, where I did it like this to show how the working is going to be, right? So the end result is that the vectors actually line up with your standard axes, right? But that's not always the case, right? You can have mutually orthogonal vectors in R3, right? And I think we saw an example of that, where your vectors do not necessarily need to line up with your standard axes like these, like this. Right, so let's see if we can get an idea how Gram-Schmidt works, right? So I have some basis to start off with, right? And what I want to do is I want to transform the basis so that I get a new basis where the vectors are mutually orthogonal, right? Okay, so the method is this, right? The U1, U2 to UM, right? So the U's are denoting my original basis, and the V's over here are denoting I'm gonna form the new basis here, right? Okay, so the process works like this, right? The first new vector V1 is not really new; it's just the same as U1, right? Okay, the second one, the V2, right? What you're doing is you're taking the second vector over here, right? The U2, and you're subtracting off the projection of U2 in the direction of V1, right? So to get the V2, right, what you do is you take the old U2 and you subtract off a projection, right? Okay, and to get the V3, right, what you do is you take the old U3, and this over here, what you're doing is, in fact, you subtracting the projection of the U3 into the subspace spanned by V1 and V2, right? So again, to get the V3, you take the U3, right? You take the third one, and you subtract off a projection of U3 into a certain subspace, right? And this is how it really goes, right? Given the U's over here, right? Given the U's, right? So if you, the first, how you get the V's is the first V1 is equal to U1, right? The second V2, you take the second U2, right? And you subtract off a certain projection, right? And the third V3, right? The V3, right? You take the U3 and you subtract off a certain projection, right? Okay, now you're using your Gram-Schmidt to obtain your new basis here. The V's here is really you taking the U's here, the original basis vectors, and you subtracting off projections from them, right? Okay, so next thing you want to notice, you want to recall that what this is this here, for example, this PV1U2, right? What this is this is a projection of U2 onto the subspace spanned by V1, right? Okay, and the formula for that, we saw that already, right? The formula for that to work out your projection here, right? The projection of U2 onto subspace spanned by V1, right, would be inner product of U2 with V1 divided by the inner product of V1 with itself, right, multiplied by the vector V1, right? So this formula for my projection over here is this ratio of inner products times this vector. Okay, so let's apply Gram-Schmidt to this basis here, right, to get a new orthogonal basis, right? Right, so how it works is for given the U1 over here, right, the V1 is actually equal to U1, right? Okay, so this is my U1 to start off with, which is the 200, right? So the first thing in Gram-Schmidt is the first element of my new basis V1 is in fact equal to the first element of my old basis U1, right? Okay, so the V1 is equal to U1, right? And now let's work on getting the V2, right? Okay, so what is U2 over here? Right, so this is the U2, right? This is U1, which is equal to V1, and this is U2, right? This is 110, notice it's in the XY plane, right? Okay, so this is the U2, and using this U2, I'm going to construct the V2, right? Now, to construct the V2, right, what I'm going to do is take this U2 over here, and I'm going to project into the direction of V1, right? Okay, so that is what this is over here, right? This is U2, and this here, this second expression over here with the ratio of inner products times V1, right? This is projection of U2 into V1, right? So what's the projection of U2 into V1? The projection of U2 projection of U2 into the direction for V1 is this blue vector here, right? Okay, so this is your projection, right? So this is the U2 over here, this black one here, right? And this ratio of inner products times a vector v1, right? This is your projection here, right? So this is the projection, okay? Now, what you're going to do is, for the U2 here, you're going to subtract this projection, right? So subtracting your projection, which is this blue arrow, means that I'm starting over here, going in the opposite direction of the projection, and then adding it to the U2 here, right? So that would have the result of subtracting this projection. So going from here, this is a subtraction of the projection, plus the vector U2 here, right? And what do I get now? Okay, so what I get when I subtract your projection, right? The projection of U2 onto V1, which is this blue one, right? When I subtract that from the U2, right? In other words, negative of the projection plus the U2 gives me this yellow vector here, right? And this yellow vector is the V2, right? And what you want to notice is this V2 here is in fact perpendicular to the V1, right? The V1 is in this direction, right? In the direction of the blue arrow. Okay, so this is the V1 here. The V1 is 200, right? And what you want to notice is this yellow V2 is now perpendicular to the V1 here, right? Okay, so let's look at it this way, right? This black one over here, this is the U1. This black one over here, this is the U2, right? Okay, and the U1 and the U2 were not perpendicular to each other, right? Okay, so why they weren't perpendicular to each other is this U2 over here actually has a certain component that is in the direction of the U1 over here, right? Okay, so in order, if we wanted to get something that is actually perpendicular to this U1, which is the same as V1, right? If I wanted to get something that's perpendicular to it, right? I can't use this U2 because it has a component that is in fact parallel to the U1, right? And that component is in fact this blue part over here, right? So what I do is for the U2 here, I get rid of that component, right? The component of U2 that lies in the U1 direction, right? And getting rid of that component is basically, well, that component is the projection of U2 onto V1, right? So by subtracting that projection from U2, I'm getting rid of the component that is in the direction of U1, right? So I'm getting rid of this piece over here from U2. When I get rid of this piece here, right, from U2, what I'm left with is I'm left with this yellow vector here, right? And this yellow vector is in fact perpendicular to the U1, which is the V1, right? So from the U2, what I did is by getting rid of the projection, I end up with something that is in fact perpendicular to the U1. Okay, so far what I have is I have the V1 and V2, right? The V1 is the U1, right, which is this original black vector over here, right? And the V2 is the yellow vector here, right? Now what I will do is, for simplicity, I will move this V2 over here and just line it up with my y-axis, right? This is actually parallel to the y-axis. I'll just have it start at the origin. It doesn't really make a difference where it starts off with, but remember, for the vector, I want the vector itself, right? So it's better if I just think of it as a position vector, right? So this vector over here, I'm gonna just move it so that it starts at the origin. Right. Okay, and as it is over here, this is the vector 0, 1, 0, which is the V2, right? Okay, so when you subtract the vectors, and I got this this vector over here. Notice this vector is the 0, 1, 0, right? But having it over here like this, it's a little confusing, right? This is 0, 1, 0. And in order to view it properly, I just move it so that it starts at the origin. Okay, so I have the V1 over here, and now I have the V2 over here, right? This over here was the U2, so let's get rid of that U2, right? Okay, so let's get rid of the U2. So in this picture over here, what I have is I have the V1 and I have the V2, right? Okay, so I have the V1 and V2 so far. Now let's work on getting the V3, right? To get the V3, I get the V3 from U3 over here, right? From my original U3, which is this U3 over here. So I'd need to plot the U3, and the U3 is, this is U3 here. Okay, so that's the U3. And how I'm going to get the V3 is I'm going to subtract off a projection, right? Okay, so for the U3 here, what I will do is I will take this U3 and project it onto the span of V1 and V2, right? Now V1 and V2 span the XY plane, right? So I'm going to take this U3 here and project it onto the XY plane, right? That is what this over here, this expression is doing for me, right? It's a projection of V1 and V2, a projection onto V1 and a projection onto V2, and you add in these. And overall, what this is doing for me is this is giving me this part over here, the negative here and the negative here. These two together are giving me a projection onto the XY plane, right? Okay, so I'd want the projection onto the XY plane. Which is this here, right? Okay, so one more time, this is the V1, this is the V2, right? This is now the U3, and I'm going to work with this U3 over here, right, to figure out what the V3 is, right? Okay, so from the U3, what I do is I take the U3 and I project it onto the span of V1 and V2, right? And that projection of U3 onto the span of V1 and V2 is this blue vector here, right? Okay, so notice your blue vector, it lies in the XY plane, right? Okay, and in order to get the V3, what I want to do is I wanted this U3 over here, I'm going to subtract off this projection, right? Because what I want is I want a third vector that's actually perpendicular to the XY plane, right? And this is the component of U3 that is in fact along the XY plane, right? So if I get rid of this over here, I get rid of this blue component of the U3, right? Then that would give me something that's in fact perpendicular to the XY plane, right? So I want to subtract off that projection, right? And when I subtract off that projection, I will get this here, right? Okay, so notice what this is, right? This is negative of the projection plus the U3 here, and this gives me the required V3. Okay, so this is the U3. The U3 is this black guy over here, right? Okay, the blue one here, the blue is the projection onto the XY plane, which is the sum of these two here, right? Okay, and when I take the sum of these two over here is the projection, right? So over here what I'm doing is I'm subtracting the projection. So if I subtract the projection, I'm taking the negative of this vector, right? And then adding it to U3, which is going up this way. And this gives me the V3, right? And you want to notice now that the V3 is in fact perpendicular to the other two. Okay, and what I really just want is the information from the vector. So to avoid confusion, I'll just take this and just start it at the origin. Okay. Right, so, and I'll get rid of the projections, and I'll get rid of the U3. So this is the original U3, and this is the projection of U3 onto the subspace spanned by the v1 and v2. So I'm gonna get rid of these. Okay, and what I'm left with is I'm left with the v1 over here, right, which was equal to u1, the v2, which I constructed from the u2 by subtracting off a projection, and I get there the v3 over here, which I constructed from the u3 by also subtracting off a projection, right? Okay, so the original u1, u2, and u3 were not orthogonal, right? But now the new basis, the v1, v2, and v3, are in fact mutually orthogonal. Alright, so I just showed you, well, I gave you an interpretation of how the Gram-Schmidt works by subtracting projections, right? But let me actually just go through this calculation here, right? Which is the same example that I just did, right? Okay, so I have the this basis here of R3 to start off with, right? So I have a basis to start off with, right? And then what I want to do is I want to apply Gram-Schmidt to get an orthogonal basis, right? So I'm going to go through my Gram-Schmidt process over here, right? So from the U's over here, and I have 3 U's, what I'm going to now get is I'm now going to get 3 V's, right? Okay, so the first V is really just the first U, right? So V1 is equal to U1, that is what this is saying over here, right? Okay. And the v2, right, you get from u2, right, the v2, this v2 here, you get from u2, and then you subtract the projection, right? And this is your formula for the projection, right? What you're doing is subtracting the projection of u2 in the direction of v1, so that's inner product of u2 with v1, and then divided by inner product of v1 with itself times the vector v1, right? And here I work out the inner products, right? The top inner product works out to be 2, the bottom inner product works out to be 4. That's against the vector v1, which is from over here, 2, 0, 0, right? Okay, so this is a half of 2, 0, 0, right? And half of 2, 0, 0 is 1, 0, 0. So I have vector 1, 1, 0 minus vector 1, 0, 0, which gives me 0, 1, 0. So that's the v2. Okay, and now I need the v3, right? And I get the v3 from using u3, right? So the v3 is gonna come basically from u3, and then using my answers for v1 and v2 from above, right? Okay, so formula, it is v3 is equal to u3, and then what you do is subtracting off projections. This one over here is projection of u3 in the direction of v1, right? And this is projection of u3 in the direction of v2, right? Okay, so again you work out your inner products, u3 with v1, right? And v1 with itself, u3 with v2, and v2 with itself. When you work out this inner product, you get 2. When you work out this inner product over here, you get 4. When you work out this inner product here, you get 2. When you work out the one on the bottom here, you get 1, right? So you're going to get a half times vector 2, 0, 0, right? And then minus 2 times vector 0, 1, 0, right? So I get 1, 2, 2 minus vector 1, 0, 0 minus vector 0, 2, 0, which gives me v3, which is 0, 0, 2, right? Okay, so this over here, the v1, v2, and v3, this would be my required orthogonal basis, right? And you can see that these are mutually orthogonal. If you take the inner product of any two different ones, you will get 0, right? Okay, so this is an orthogonal basis for my R3 that was constructed from my original basis here. This one to start off with was not orthogonal, right? But this one now actually is orthogonal, right? Okay, and then we have what is orthonormal, right? So this is orthogonal, but it's still not orthonormal because if it was orthonormal, each one would have to have length 1, right? Now this is okay, this second one has length 1, right? But this first one over here has length 2, right? Okay, so from if I have an orthogonal basis that isn't necessarily orthonormal to start off with, what I do is I just divide each vector by its own length, right? Okay, so if I have a vector and I want to make it a unit vector, in other words, I want the vector to have it. I want to get a new vector in the same direction but with length 1. I take the vector and I divide it by its own length, right? So this 2, 0, 0, I'm going to divide it by its own length. And the length of this vector here is 2. So if I divide the 2, 0, 0 by 2, I'm going to get 1, 0, 0. Likewise, over here, this 0, 0, 2 has length 2, so I divide it by its own length to get 0, 0, 1, right? And now what I have is an orthonormal basis, okay? Right, so the Gram-Schmidt first gives you an orthogonal basis, and what you do is you just divide each vector inside your orthogonal basis. Divide each vector in your orthogonal basis by its own length in order to get an orthonormal basis. Okay, so let's look at orthogonal matrices very briefly, right? So if I have a square matrix is called orthogonal, right, if the inverse of a matrix A is actually just equal to the transpose, right? Okay, and here I have some properties or characterizations of an orthogonal matrix, right? Okay, so if A is an orthogonal matrix, and these are all equivalent, right? So this statement is equivalent, first statement is equivalent to second statement, and so on, right? Which means that if, for example, I have a matrix that satisfies this third condition here, right? Then that would mean that the matrix is orthogonal, right? Okay, and conversely, if I have an orthogonal matrix, then it always satisfies condition 3, right? Okay, right, so if A is an orthogonal matrix, then A times A transpose is equal to the identity, and that's not really a big deal because A transpose by definition is equal to the inverse of the matrix, right? So A times A transpose is the same as A times A inverse, right? And if you multiply a matrix by its inverse, you get the identity, right? So that's really what's going on over here. It's just using the fact that if it is orthogonal, that A transpose is equal to A inverse, right? A little more interesting is that if A is an orthogonal matrix, then your rows of A form an orthonormal basis for Rn, right? So it's probably easiest if you see an example of that, right? Okay, so consider this matrix over here, right? This is an orthogonal matrix, right? Now let's look at the rows and let's see if the rows satisfies condition 3, right? Well, your rows over here, they're linearly independent, right? Because of the position of the ones and the zeros, right? If you have 3 linearly independent row vectors here, right? Then they're going to span R3, right? That is, in fact, using Goldilocks principle, right? Or you could just check to see that these 3 also span R3, right? So these 3 row vectors are linearly independent and they span R3, right? You want to notice that they actually row vectors, if you consider the dot product of 0, 1, 0 at 1, 0, 0, right? That dot product is 0. And likewise dot product of 0, 1, 0 with 0, 0, 1, right? And dot product of the second row vector with the third row vector, right? So your vectors over here are your row vectors are mutually orthogonal, right? And each one has length 1, right? Clearly, right? The length of each row vector here is 1, right? So your row vectors here form an orthonormal basis for R3, right? This is a 3 by 3 matrix, right? Okay, so your row vectors form an orthonormal basis for R3, and that's an example of a condition 3 holding over here, right? So what that means is that this matrix here is an orthogonal matrix, right? Okay, and then we also have this condition here that the columns would form an orthonormal basis. So it's the same idea, but now you're looking at the columns, right? So if you consider the columns here, your 3 columns are 0, 1, 0, 1, 0, 0, and 0, 0, 1, right? These columns are going to form a basis for our tree. Clearly, each column over here has length 1. And if you take inner product of, you take the dot product of any two different columns, you will get 0, right? So the columns would form a basis from our tree, assuming that you're writing R3 as now column vectors, right? Okay, so your columns form a orthonormal basis for R3, and that would mean that your matrix A is an orthogonal matrix. So that's examples of 3 and 4, right? You can check for this matrix B over here that the rows, the row vectors here, your 3 row vectors, would form an orthonormal basis for R3, and likewise your column vectors here would form an orthonormal basis for R3 when you write R3 in terms of column vectors. Alright, so we saw previously that if I have a vector v, right, and I want to project into a one-dimensional subspace, right, and this one-dimensional subspace is spanned by vector u, right, then the projection, so the v over here is the green vector, right, the vector u, right, is this gray vector here, and the actual projection is your red vector, right? So this is the projection. The red vector is the projection of v in the direction of u, right? So what you're doing is you're projecting v into a one-dimensional subspace here, right? And this red vector is your required projection, right? Your formula for getting that projection is given by this here, right? A ratio of inner products times the vector small u, where u, this one-dimensional subspace, is spanned by the vector u, right? Okay, so this is projection into a one-dimensional subspace. If I want to project into a subspace that isn't one-dimensional, so for example here, this is a projection of vector, this black vector here, right, into this subspace here. This subspace is two-dimensional, right? Okay, it may seem like a reflection, but that this yellow vector, which is the projection, is actually lying in the subspace, right? Because you can see that, look at it this way, right? It's actually contained inside the plane. So the yellow vector is contained inside the plane, right? Okay, so what I want is a projection of a vector v to start off with. I want to be able to get the projection, but now a projection into a subspace that isn't necessarily one-dimensional. It could be two-dimensional or higher, right? Alright, so a formula for calculating projection of a vector such as this black vector v, right, into a subspace such as this plane u over here, right? Formula is, well, what I would need is I'd need an orthonormal basis for the subspace u to start off with, right? Okay, so subspace u, for example, this plane over here, right? So I have some finite dimensional subspace, right? And if I have an orthonormal basis for my subspace here, such as the u, right? Then how I would calculate the projection of the black vector v, right, into the subspace, right? So the orthogonal projection would in fact be the yellow vector here, right? In this example, right? How I would calculate this yellow vector projection is via this formula here, right? Okay, now this is the basis for the u here needs to be an orthonormal basis for this to work, right? Okay, so what I do is I just take the inner product of the vector v that I want to project with first basis element, right? And then multiply against the basis element. Then take the inner product of vector v with second basis element, multiply against your second basis element, and I keep going like that, right? And I do that for each of the basis elements in my orthonormal basis for u, right? Okay, so let's see an actual example of calculating that, right, for a certain subspace. Okay, so consider this example here. I have a subspace in R3, right? It's a two-dimensional subspace because you have two elements in your basis here, right? So this subspace is going to be a plane in R3, right? And it has an orthonormal basis, which is, well, 0, 0, 1, right? And 0, 0, 1 is a vector in your z direction, right? And a vector 1 and root 2, 1 and root 2, 0, right? So you want to notice that both of these components are the same, and the z component is 0, right? So because the z component is 0, this is lying in the xy plane, right? This vector is lying in the xy plane, right? And the x is equal to y, right? So this vector over here, 1 and root 2, 1 and root 2, 0, right, is in fact a vector that is in the direction of this edge here, right? Moving away from the origin, right? So it's moving like this here, right? Okay, so these two vectors here, these are an orthonormal basis for a certain subspace, right? You don't need to sketch this diagram to actually see, right? Matter of fact, they're just giving you the information that I have a subspace U with a certain orthonormal basis, right? And what I want to get is I want to get the projection of a vector into this subspace here, right? Okay, so I can work out everything from the information given to me, right? I don't really need this diagram, but the diagram is so that you can get a picture of what's going on, right? Okay, so the U over here, the subspace U, is this plane here, and this plane, we saw this already, right? Your plane over here, you can identify with, well, the plane actually is y is equal to x, right? So the subspace U, you can identify with your plane y is equal to x here, right? Okay, and what we want is projection of the vector 1, 0, 1, right? And this black vector here, that black vector is a vector 1, 0, 1, right? And what we want is we want a projection of this black vector v, right, which is the 1, 0, 1, into the subspace U, right? And the required projection would be a yellow vector here, right? Okay, so how we work out what the projection is you use your orthonormal basis for your subspace, right? All right, this has right. Okay, so it's your vector v, right? Take the inner product with your first basis vector, right? That's given to you, and remember these bases, this basis here is an orthonormal basis, right? So take inner product with your first basis vector and multiply it against the basis vector. Take inner product of vector v, right, with the second basis vector, the u2, right? Multiply it against the u2, right? Okay, so this is just working out the inner product, right? The v here is 1, 0, 0, 1, right? The u1 is this first vector, 1 and root 2, 1 and root 2, 0. And you're taking the inner product of that. When you take the inner product of that, you're going to get 1 and root 2, right? And you're multiplying that by the vector 1 and root 2, 1 and root 2, 0, right? Okay, and then you take the inner product of the v here with u2, right? And this is the u2 here. So the v is 1, 0, 0. The u2 is 0, 0, 1, right? Take your inner product here, you get 1, right? And then you're multiplying it against the vector u2, right? Okay, and then you just work this out. So it's a scalar over here by this vector, right? So each of your components over here you multiply by a scalar 1 and root 2. So you get a half, 0 here. And here you get 0, 0, 1. And then finally you just add these two vectors to get you half, 1, right? And that half, 1 is your yellow vector inside here, right? Okay, so the black vector is the v, right? This blue plane over here is a subspace U, and your required projection of v into U is your yellow vector here.